Thank you for tuning in. The topic of this video is going to be about the digital camera on your TEM and specifically its basic operation and as well as some general guidelines for how to use it. So just as a disclaimer, please consult your manufacturer's instructions or manual for your digital camera. The general guidelines we're going to go over today are basically universal, but obviously shouldn't take precedence necessarily over manufacturer's recommendations. So please keep that in mind. The camera that we have on here is a Gatan UltraScan 1000p, which is no longer actively in production, but does have a manual with it. And of course, it sounds obvious, but I would always recommend that you consult your equipment manufacturer's manuals. So now that we have that out of the way, the first thing we can talk about when referring to TEM cameras is where are the cameras located. So there's two places that the cameras are located. So one here's the viewing screen, okay, the projection chamber. So one place that they're located is here on the side. And we call those side-mounted cameras, obviously. So this is actually a port where a digital camera could be mounted. Okay, on this side, this isn't a camera. This is a stem detector, but that takes the other or place of the other side port. So the other place that the cameras are mounted, and this is typical if you're doing physical sciences or material science work, is underneath the viewing screen. So if we come down here, okay, so that is the digital camera right there, and so that's referred to as a bottom mounted or on axis camera, okay, because literally it's right in the beam path, although it can be pneumatically inserted and extracted. So the difference between the two, if you mount the cameras above the screen via side mount like this, you get a larger, or I should say, you have larger effective fields of view than if you mount underneath. So if you're doing applications that generally require large fields of view, it's obviously beneficial to have your camera side mounted. If you're doing applications that require smaller fields of view, then bottom mounted is usually preferred. Generally speaking, if you're doing physical sciences work, then you're probably working with a bottom mounted camera because that's more suitable for doing things like high resolution imaging or lattice imaging. That's not to say that you couldn't necessarily do them with a side mounted camera. It is possible to do that with a side mounted camera, but it's generally done more frequently with a bottom mounted camera. If you had to pick between a side and a bottom mounted camera, it's always better to have something bottom mounted than side mounted. So you have more versatility with something that's bottom mounted than you do side mounted. You can still get a fairly large field of view with bottom mounted, not to say that you couldn't do it. Not to the extent that you had with a side-mounted camera, but that's not to say that you're limited to only extremely small fields of view with a bottom-mounted camera. Another thing to keep in mind, so this is, again, this camera is a bottom-mounted camera. It is specifically designed for that, so if I got bored and said I want to take this guy off and side-mount it, I couldn't do that. So this is actually physically built to be a bottom-mounted camera, and pretty much all cameras are like that. They're either physically configured to be mounted like this or to be mounted up here on the side, and they're not interchangeable. Some microscopes will have both a bottom-mounted camera and a side-mounted camera. On this one, we only have the bottom-mounted camera. So now that we covered the basics of where the camera is located and what that entails in terms of benefits and or drawbacks, the thing to keep in mind about your camera is that it has a dynamic range. So dynamic range is just a fancy way of saying what's the difference between the lowest intensity that it can detect and the highest intensity that it can detect. So there's different ways to assess this with a digital camera. The most common way of doing it is with what's called grayscale values, which can be expressed in terms of bits. So in other words, if I have a camera with an 8-bit dynamic range, then I have 2 to the 8 possible grayscale values that camera can detect in its images. Okay, so now if I have 16 bits, then I have 2 to the 16. So the difference between 2 to the 8 and 2 to the 16 is several orders of magnitude. So with 2 to the 8, that's 256 grayscale values, and with 16-bit, that's more than 65,000. So the way that's usually expressed then, because we're talking in terms of grayscale, is the smallest value would be pure black, and the highest value would be pure white. Okay? So this is a 16-bit camera, and because of that, it is capable of detecting between 0 and 65,000 grayscale values, again from peak black to peak white. So that is the concept of dynamic range. Obviously, more is always better because that allows you to capture a greater range of intensities in your image than if you had a camera with lower dynamic range. Pretty much all cameras that are made now are 16-bit dynamic range. Okay, so I have a cerium oxide nanoparticle sample inserted with the particles dispersed on a lacy carbon support film, and I have the microscope set up for a bright field image at an indicated mag of 13,500. So we'll go ahead and pull this up on the digital camera and look at a live image. Okay, so I'm in the camera tab. Make sure you have Gatan selected and then search. Okay, and now we're going to listen. There's the noise for the camera inserting. I then have to lift up the viewing screen because I have a bottom mounted camera. If I didn't have a bottom mounted camera, I wouldn't have to do that. Okay, but the screen is in the way. Okay, and there is my live image. So the key parameter when you're live imaging is the exposure time, and that literally is how long your camera collects signal before it generates an image. So right now it's only collecting signal for 1/100th of a second before it generates an image. So the exposure time in general, if I increase it, is beneficial in the quality of the image. Okay, so if I actually, I'm going to put the screen back down here for a second. Okay, if I put the screen back down, you'll notice that I still see some speckling, okay, in the image. This is noise. Okay, so this is what I get even when I don't have a beam on the camera. Okay, so if I take and lift the screen up, I see the image, but I still have a contribution from the noise to that image. Okay, so the key then is I want the signal, which is the good part of this, to outweigh the noise. Okay, and so the noise itself is not really dependent on the exposure time, but the signal, or the good part, I should say, the good part of the image, which is the signal, is. So if I increase the exposure time, my signal to noise ratio improves and I get a better quality image. Okay, so if I click on view here, and then this is a shortcut, I hit up arrow, okay, it doubles it, you can see what's happening here. Okay, I'm at 0.04, now I'm at 0.08. Okay, so the image quality improves dramatically as a result of doing that. Okay, because my signal to noise ratio goes up as I increase the exposure time. Okay, now when you're live imaging, I usually don't go above 0.1. Okay, that's a personal preference. I usually don't find that it's necessary to go higher than that. Again, when we're talking about just general bright field and or high resolution imaging, under certain conditions you may have to go longer than that. Okay, but for just general bright field high res, I find that that's usually sufficient, again under the assumption we're operating at spot size 1. Okay, but one of the things you can see here, if I go to the joystick, I want to move around. Okay, I have a little bit of a lag here because I have a longer exposure time. Okay, so if I go back down to 0.01, I do 3 down clicks of the arrow. Okay, I have a bad signal to noise ratio, but my camera response is a lot better. Okay, so if you're trying to move around quickly and just find an area, it's usually good to just use a shorter exposure time. But once you've found your area and you want to actually see it in some meaningful way, you can go back to something higher. Again, I usually use 0.08 as a live exposure time. Okay, so now your camera has a dynamic range right now, which is expressed in grayscale values. If I want to see that representative, what is representative of that in the image, I come here to Analysis Histogram. Okay, I get a histogram here of the live image. So what is the histogram telling me? The y-axis is a little misleading, okay, because what this should say is number of pixels. So even though it says counts, that's number of pixels. This is a 4 megapixel camera. Okay? What I have on the x-axis is a little bit more meaningful. Okay, what I have on the x-axis is an expression of the dynamic range in the image. Okay, so obviously 0, right? I can't go less than that. Okay, that would be no signal. Okay, and then over here, this would be the max signal. Okay, or grayscale value. Again, I get 65,000 grayscale values here. So you can see this is oscillating between 12,000 and 14,000. Okay, again, because I have some variation in the signal, so this does oscillate a little bit. Okay, now you can actually take a look at this. If I go back down, I'm at 0.08. If I go back down to 0.01, okay, you'll notice my max grayscale value went down, okay, because the max signal went down. So that max grayscale value is linearly, approximately anyway, linearly scalable with exposure. Okay, and it's a little hard to see that right now because I have a high, or a low I should say, signal to noise ratio here, which is why you're seeing this histogram oscillate all over the place. Okay, so you see less oscillation. If I double it now, okay, you can see that even though this is oscillating, this max value went up. I double it again, max value goes up again. Okay, my signal to noise improves. I go up again, and now you can see it's approximately doubled. Okay, the max counts went from 6,000-7,000-ish to 12,000-ish, 14,000-ish. Okay, so that's another key thing to remember with most digital cameras is they have a linear response. So your max signal scales linearly with the exposure time. So the histogram is useful for another reason, because it allows you to make sure that you are not exceeding the dynamic range of the camera. If you exceed the dynamic range of the camera, you risk damaging it. Okay, that would be the equivalent of if I took a really, really bright light and I shined it in your eye. If it's too bright for your eye, then your eye is going to get damaged. The same way with the camera on the TEM. Okay, so that is again reflective in this max value here. So again, my max value is about 65,000 counts. So as long as I don't get anywhere near that, I'm in no danger of damaging the camera. Okay. So the question then becomes, if I'm in no danger of damaging the camera at 65,000 counts, how high should I get my max counts? Okay? Your signal to noise always improves as you go up. Okay, so if I double this again, okay, image is still looking better. Okay, but can I really see a big difference here? If I go back down, I mean, it does look a little bit better. It's not really a huge difference, but it does look a little bit better. Okay, you can see now my max grayscale value is about 25,000-ish. Okay, generally speaking, with most digital cameras, the optimal grayscale value range is around the middle value of the dynamic range. Okay, so in other words, if 65,000 is the max, I'm shooting for something in the vicinity of 32,000. Now in practice, I usually don't have to go that high to get a decent image. Okay, I usually don't have to go that high. I can just visually inspect the image and make an assessment as to whether or not it has a suitable signal to noise, and usually my eye is pretty good at telling me that. Okay, so even though theoretically it would say I need to go higher, okay, I may not need to do that. And there's actually a very good reason for doing that we're going to talk about here in a minute. Okay, so I'm going to go back down to 0.08. Okay, so now of course this is a live image. Okay, the live image uses what's called binning, which is a fancy way of saying that the pixels are grouped together in your camera, which reduces the effective pixel size. Okay, so your live image here is not necessarily representative of your final image or your acquired image. Okay, so your acquired image on this camera is set up so it uses the full, or I should say the smallest possible pixel size. Okay, so as a result of that, I end up with approximately 16 more effective pixels, 16 times, I should say, more effective pixels in the acquired image than the view. So that translates into, in terms of the exposure time, I have an exposure time here in acquire and view. If I want to get counts in the acquire that are similar to what I get here, I have to change this number, or I should say multiply this number by 16 theoretically. Okay, so in other words, if I have 0.1, because that's just an easy multiplier here. Okay, if I have 0.1 and I want to get an image with the same signal to noise in my acquired, because the acquired has 16 times the pixels, I've got to use 0.16. Okay, so if I have 0.02, I've got to use 0.32. Again, theoretically. Okay, generally speaking, I use a multiplier of about 10. Okay, so if we go back to 0.08, okay, I'll use a multiplier of about 10. I've got 1 here, and that usually works well. Okay, that's a little less than 16, but you'll see here it does produce a good image anyway. Okay, and there's the final image. This is, again, the full 4 megabyte image, and this does have a sufficiently high signal to noise ratio. Okay, so I increased my indicated magnification to 350,000, and I changed my objective aperture so I have a high resolution condition now. You'll notice though that my area of illumination on the screen here is approximately the same. So again, with this digital camera, the field of view corresponds roughly to the diameter of that outer circle. Okay, so in other words, even though I change my indicated magnification, as long as I keep the projected illuminated area on the screen about that size, I should still end up with the same signal on the camera. Okay, so I'm going to go ahead, lift up the screen again, still have the camera inserted. Okay, but now we see a high-res image. So now there's some additional considerations to keep in mind when you're high resolution imaging. Okay, so you have the same concept of signal to noise that you do if you're doing just low magnification imaging or bright field imaging. But now an added problem that you have to consider is that specimen instabilities are manifested much more strongly at high magnifications. And so when we're talking about sample instabilities, we're talking about drift and or vibrations. Okay, so I don't know if you can see it, but every time I talk, right, there's a movement to the sample. Okay, so obviously you don't want to do that while you're imaging at high resolution. Okay, and obviously that's easy to alleviate. Okay, but one thing that you can't always alleviate is specimen movement, okay, or drift. So that tends to get better the longer the sample is left in there. So if you leave the sample in there for a long time, the drift will tend to stabilize and become almost minuscule. Okay, but the sample is moving. Okay, there's actually no question about it. Okay, so what this means then, in effect, is if I want to capture an image at high magnification and it not be blurry, I may have to sacrifice some signal to noise for the sake of getting a non-blurry image. Okay? So I'm going to be quiet here for a second. I've got 1 second here. Okay? That's usually as high as I go when doing a high-res image. Okay, but what I'm going to do here, I'm going to be quiet and do an acquire. Okay, so we have a nice high-res image here. It's not blurry at all. Okay, but if I do the analysis histogram, okay, I'm not getting higher than about 8,000 counts. Okay. So I'm nowhere near the middle of the dynamic range. Okay, so in theory, if this is 8,000, if I triple the exposure time to 3 seconds, okay, I should hit the middle of the dynamic range and get a better quality image. Okay, the problem if I do that though is if the sample doesn't sit still over that 3 seconds, I'm going to end up with a blurry image. Okay. And I don't care how good your signal to noise is in the image, if the image is blurry, it's not usable. Okay? So we can do the exercise here. I'm gonna put in 4, just for the sake of argument, okay? And then I'll be quiet, and we'll see how it looks. Okay, so that's a 4-second exposure, and I hope you can see that, but that's blurry. Okay, that's a blurry image. That's the one we took with 1 second. Okay, so now if I look at the histogram for this, I've got way higher counts, closer to the middle of the dynamic range. So my signal to noise is way better in this image, okay, than it is in the shorter exposure. But the consequence of that, because the sample isn't sitting still perfectly, and again, look at the scale bar, that's 5 nanometers. Okay, you don't need a lot of movement at these kinds of field of view to get a blurry picture. Okay, but a consequence of that is my image is now blurry. Okay, so that really didn't do me any good. Okay, so when you're doing high-res imaging like this, more is better with the exposure time until you get to the point where you get a blurry picture. Okay? And at some point, again, if it's you may get a benefit by increasing the exposure time and signal to noise, but you may end up with a blurry picture. Okay? In some instances, with this microscope, I find that 1 second is usually sufficient, okay, for doing lattice imaging like this. There may be times where you have to go less than that. You have to go half a second. Even if I do half a second here, come back here. Yeah, you can see how it's moving? See where I'm looking? It's not the same area, okay? So sample's got a little life to it. But I'm gonna do half a second here. Okay, so that's half a second. All right, so again, looking at the histogram, again, I've lost a lot of dynamic range here. Okay, I'm only going to around 4,000 counts, but this is still a way more useful image than this. Okay, although if we look at this, right, that's 1 second, that's half a second. Okay, 1 second image is a lot better. Okay, so I did get a benefit by doing that, but again, I didn't exceed the time scale over which I start to see instability in the picture. Okay, so I switched specimens, and now I have a silicon single crystal specimen in. So there's some additional things to discuss when working with the camera when you're recording diffraction patterns, and specifically diffraction patterns from single crystal specimens. So in the video I recorded on selected area diffraction, a lot of this is kind of review of that, but you need to make sure use a high numerical spot size, use a selected area aperture, and we do have the beam stop inserted here. So when we talk about recording images, conventional images, bright field, high resolution images, we're more or less not overly concerned with damaging the camera. It's very difficult, unless you're being extremely negligent, to damage the camera while acquiring a conventional image. What you tend to be more concerned with when you're choosing an exposure time is making sure you get adequate signal to noise, but you're balancing that out against instabilities of the specimens. Okay, in other words, drift, as we saw before. When you're collecting a selected area diffraction pattern, particularly from a single crystal specimen, your overwhelming main priority has to be not overexposing the camera, not exceeding the dynamic range of the camera. It's very easy to do that when you're collecting diffraction patterns, because you are putting a lot of signal into really small areas, okay? Those focus spots in the DP. So I've already got the DP set up. I'm just going to go ahead and lift up the viewing screen. I've got a live image here. My exposure time is set to 1/100th of a second. I do have a beam stop there. Okay, you can't see it, but it is in the middle. It is covering the direct beam. Okay, and I've got my histogram going right now. So right now, my max counts in the histogram isn't really getting close to 1,000. Okay, so I'm well under the orders of magnitude below the limit of the dynamic range. So I'm going to do a test exposure here. Okay, I'm just going to do, we'll do 0.1 seconds. Okay, and we're going to see how this looks. Okay, so you can see it's very noisy. I can see the spots, but what I want to do now is, if I do analysis histogram, okay, I can see now in my histogram my max counts is around 1,200. So again, the camera has good linearity. So if I go to say 1 second, this should get me to around 12,000 max counts, which is still well below the max dynamic range. In fact, it's more like 20% of the dynamic range. Okay, and that will improve my signal to noise. So I'm going to go ahead and close this. I'm going to go ahead and change this to 1, and we'll do an acquire. So again, more is better in terms of signal to noise, but you have to be careful now that you're not exceeding the dynamic range. So this obviously looks a lot better. And then if I do analysis histogram, so now my max counts is around 20,000. Okay, so that's still under half of the dynamic range. So realistically, I could go to 2 seconds here. Okay, and I should get to a max of around 40,000, and that should still be safe. Okay, because again, the cutoff point on here is about 65,000. So I'm going to double this. Okay, because again, longer means better signal to noise. Okay, and that looks better. I do analysis histogram. Yeah, so I'm about 45,000 max, again, which is still, that's about 3/4 of the dynamic range, so that's still safe. I have no danger of harming the camera from doing that, okay? So again, the same basic idea applies when you're collecting diffraction patterns, right? Longer is better in terms of signal to noise, but you have to balance that against potentially damaging the camera. We're not, like when we're collecting an actual image though, we're not really concerned with things like drift, okay, because this isn't like a high resolution image. We're looking at a really small field of view. This is a diffraction pattern. So if the sample moves, you know, a few nanometers within the exposure time, that really isn't going to have a large impact on this pattern, okay? So we can afford to use something that's maybe a little bit longer. I wouldn't go longer than 2 seconds on this. If I go to 3, for example, I'm probably gonna exceed the dynamic range, and then that would be a problem, okay? So that's a basic synopsis of how to choose exposure times when you're recording data, both images and diffraction patterns. If you have any comments or questions, please feel free to leave them in the comments section below. If you have a topic that you would like to see covered, also please feel free to ask me about it. Thank you for watching.